Oh yeah, Wendy's here. We're almost on 9 years now, so that's pretty exciting. So what sets us apart from all those other locations? Well, we're interesting. We have two very good talks tonight that I'm very excited about. We're interactive. You all will get a chance to ask questions. I'll put the phone number here on the screen in a little bit. And we like to have fun. We have trivia at the end, so if y'all can stick around, we've got some. Our number one prize is back again, our lunar orbiter prints from the great Robert Reeves. We still have a whole bunch of them in the stockpile, so look forward to that. And if you haven't already, please sign up for our email list so you can continue getting information about our events. And feel free to also follow us on our socials. We're trying to keep up to date, not only about AOT, but also space things going on around that are exciting to keep up with. The other exciting thing is we announced last time, but I'll say again, especially for the new people, we have new shirts in. They are being showcased up here, Aaron and Eric. The colors, they really do pop. I'm not going to lie. They came out very good. So we have those, $20 per. We have cash and Venmo options. We will have stickers, hopefully by the next event. We've ordered them, so hopefully they'll be coming around. And those will be a donation based. But please don't use for the stickers. And then once we sell enough shirts and stickers, we'll continue to get more merch, such as maybe more glasses, pint glasses, and other things like that. So look out for those in the future. Tonight's astronomy photos, thanks to Ethan Chappell, who always has some great photos. This is deep sky object. Do you know which deep sky object? Triangulum. Very beautiful, very pretty. From Saltiano or somewhere else?
From the El Dorado Star Party.
The El Dorado Star Party. Star parties are a lot of fun. If you all ever get a chance to go to a star party, I highly recommend it because, well, you can see cool things like this. All right. This evening's entertainment. Aaron.
Yes, our first speaker of the night will be a PhD student from UTSA, Eric Austin, talking about the cosmic gunk, the secret archive inside meteorites. And then we're going to have a short break, and we're going to come back with Astronomy in the News with myself. And then after that, we're going to have Dr. Jonathan Gasser from Southwest Research Institute talking about New Horizons, a journey to the edge of the solar system. And then our typical fun trivia after that.
Today's trivia, if you have any problems with it, you have a problem with it. So all right. I'd like to welcome our first speaker up tonight, Eric Austin, who is a PhD student in physics at the University of Texas at San Antonio, where he studies planetary science and meteoritics. His research focuses on the physical properties of insoluble organic matter extracted from carbonaceous chondrites, which are ancient meteorites that preserve clues about the early solar system. By measuring how this material behaves, Eric aims to better understand processes such as dust aggregation in the protoplanetary disk, the evolution of organic matter in asteroids, and the internal structure of icy worlds. That I read that. When he's not in the lab or teaching, Eric enjoys golf. I didn't know that. We've got to go golfing. Video games and spending time with his fiancée and their 3 dogs. Please welcome Eric Austin.
All right. While he gets set up, especially for our first timers tonight, we have a little tradition here. Please be responsible. Okay, you can take to the. We have a drinking word. So Eric's going to word, and every time he says it, we'll give him a little woo and take a swig. What's tonight's drinking word?
Gunk.
Gunk.
Gunk. All right, hi everyone. I'm Eric Austin. I want to thank Aaron, Michael, the AOT team for allowing me to live out my dream of giving a talk on a last second put together presentation while drinking beer. Bear with me, let's see how it goes. So yeah, I'm gonna be covering the material that I study as a part of my PhD. I just call it Gunk. It's referred to as IOM. It's very complex chemically, and it's very stubborn to use to get measurements on in the lab, and it's very expensive and difficult to actually extract from meteorites. So it pretty much checks all the boxes as a material we want to study in the lab. So moving on, so when I say organic material, that simply is just kind of hinting it's carbon bearing. It's not necessarily alive or is associated with anything alive, so I'm not dealing with any kind of living things inside of meteorites. I deal with the specific primitive meteorites that are very abundant in carbon and therefore abundant in this organic material. And what we kind of care about is what can we learn from this material and what does it tell us about the overall kind of scope of the solar system, from how planets put themselves together to how they kind of heat themselves up in the outer solar system. So yeah, meteorites, I like to think of them as time capsules. They contain all kinds of different materials within their structure that can give you evidence of processes that meteorite has kind of been through, its history, and the carbonaceous chondrites are especially abundant in this organic material that can give us a little bit of insight into what the environment may have been like even before the asteroid or the parent body asteroid that our meteorite came from was even put together. So we can kind of use these chemical records to understand different things in the solar system, and the specific material that I'm talking about, it's called IOM, insoluble organic matter. This is the actual gunk right here. So it's insoluble because it pretty much resists dissolving in pretty much any solvent. Well, when you put the meteorite in the hydrofluoric acid that I sit there and dissolve it in, everything pretty much goes away except for this gunk. And getting it is very difficult, but it's worth it, and it's considered a macromolecular substance, meaning we can't really put a single chemical label on it. It's always going to be consisting of different kind of chemical signatures from one grain to the next, which is some of the evidence why we know it's so primitive, because when you look in one meteorite, you're not looking at all the same IOM. And then refractory just means it's stubborn. It doesn't change very easily. It doesn't get affected very easily. And this is why it's been around for billions of years, so scientists like to say. This is a little iPhone image I took myself of some IOM that I extracted. It's very, I'd say one of those is maybe like a millimeter or 10 microns across or so. They're very small grains. You get a big chunk of meteorite, you end up with very little material. I think that's from probably a 10-gram meteorite. That's all of the IOM that they were able to get, just a little bit the size of a quarter. So this IOM is important specifically because when you look at all of the carbon inside of the meteorite, you're going to find that 75 to 99% of it comes from this specific material. And so if we want to really understand how carbon has been processed throughout the history of the solar system, from tiny dust grains in the protoplanetary disk to asteroids and to icy bodies in the outer solar system, we really need to constrain our understanding of not just the chemical makeup of these material, but also the physical properties. So some of the clues that scientists have been mainly kind of working from is isotopic signatures from doing analysis of this material. Specifically, they find that it's really deuterium rich, so it's got a lot of heavy hydrogen, and it's really rich in nitrogen-15. The main point that this is telling us is that this material at some point went through an environment that was extremely cold, but extremely radiative. So it was driving chemical reactions, but the fractionation was preferring the isotopic abundances. So as we kind of think about these signatures, we can only kind of use them as like a time record. We can't really use it as GPS, so we can say, okay, it formed in cold region, but what cold region? There's the interstellar medium that would have been the cloud that the actual solar system formed from. There's the protoplanetary disk, the outer regions that are going to be super cold and support this kind of chemistry. And there's also people that argue it could also just be chemistry that was done within the parent body asteroids after simpler organics were already, or simpler gunk, if you will, was brought into the parent body asteroids. So there's a lot of different theories, if you will, that scientists use to kind of say where this stuff comes from. The main theory is that it was a very complex, gunky material that formed before the solar system formed. In the interstellar medium, you have dust grains that get coated with ice. They go through very turbulent kind of environments. They'll eventually get irradiated and form these complex organics. Those eventually get brought into the young protoplanetary disk, where they eventually end up in our meteorites that we study. That just kind of seems to check all the boxes as far as why it's deuterium rich, why it's nitrogen rich, but there's a lot of the differences in the chemical makeup between certain IOMs, especially in the same chondrite, lead them to believe maybe it's a little more complex than this. So another favorable scenario is that those simple organics from this interstellar medium is what was inherited, and inside the protoplanetary disk through different kind of mechanisms, mainly radial transfer, as dust goes inward towards the sun and kind of gets pushed back outwards towards the cold regions. They can kind of get both that cold environment and the radiation necessary to form, kind of transfer the simple organics into more complex organics, and then eventually aggregate into our asteroid parent bodies. The more complex one that chemists like to adopt is that they formed in the parent body. So everything was more or less just a process and an evolution. And this material, it's tough, but it still can be altered. So as it goes from the interstellar medium, it changes. It gets into the protoplanetary disk, it changes a bit. And then once it gets into its parent body asteroid, it'll get changed through radiogenic heating and through just basic aqueous alteration, and end up being the organics that we pull out of the meteorites. I really think it's a little bit of all of it. I think there's enough evidence as far as how they've modeled all of these different scenarios that this material that I have in my lab is not necessarily the product of a single origin story. It's more or less processed through the ages as far as when the interstellar medium was creating the protoplanetary disk, it getting pulled into the disk and being transferred and altered through those processes, and then eventually ending up in some kind of parent body with other kind of neighbors inside of there, if you will, that would give it different kind of chemical signatures based on how that asteroid was evolving over time. So the beauty of this is we kind of, you can only study the IOM so much and kind of glean so much from it. But now looking into the future, we're starting to get fresh asteroid samples that have no terrestrial contamination that are also showing these same abundances of organic materials. And we're looking forward to be able to analyze these, compare them to the IOMs from meteorites, understanding how Earth, because that's one thing we've never necessarily been able to pinpoint, how the entry into Earth and how the acid isolation kind of affects these materials. So this will give us something to compare those measurements to see if what we do in the lab or how they're affected by Earth's atmosphere and entry kind of can change those materials as well. And this is just Hayabusa and the OSIRIS-REx, where we collected samples from Bennu and Ryugu. So hopefully I'm able to score some samples from those. It's actually looking promising. And this Gunk is not only in meteorites, and this is where I try to take my measurements and expand what I can do with it. It's very abundant in a lot of bodies, pretty much all of them in the outer solar system. So asteroids, comets, dwarf planets, they all have been evidenced that they have a very high abundance of this organic material that would be pretty much like this IOM. And these models, though, run off of the physical properties. We know a lot about the chemical makeup, but we pretty much know nothing about the physical properties such as density, elastic modulus, surface energy, all the stuff that these kind of models would need to understand the processes going on in these worlds. So because they don't have those measurements, they turn to other organic materials, coal, kerogen, which is an insoluble form of coal, tholin, which is a photochemistry material that they make to study gas haze, moons and planets, and just other simple gunk, glycolic acids, just anything that's just kind of simple, and they can justify using that as their organic material just because they don't actually have any other organic to use. And what do you do in that situation? You either ignore it or you pick something to put into the model. So these are kind of an example of the different physical properties that are necessary for these models but that are missing. My research, I look into the Young's modulus, which essentially tells us how stiff the material is, the surface energy, the density. I plan on also doing viscosity. And the important thing about these measurements is we're able to get multiple data points off of single grains of IOM. So that's probably like half of a milligram that I've got embedded into an epoxy puck. And then in one of those grains, I can take 3 data points, get a depth profile, so I collect the data as a function of depth, and I can average that amongst many grains to get a really good understanding and idea of how these grains, the stiffness, and then I also do density with pygnometry, and then we'll do surface energy with atomic force microscopy. All methods that we get information from just single grains or very, very small sample sizes. So yeah, key takeaways. We got a lot of information from chemical stuff and structure, bonding information from this material, but the next gen of science, we really need to apply this to Bennu samples, Ryugu, because we've more or less analyzed all the chondrites we can with these methods and kind of giving the same information. So we're kind of extending it to get physical property data to see if we can kind of extend our understanding and use that data to kind of add to the picture of where this IOM may have came from or how it evolved over time. So yeah, Gunk.
All right, thank you, Eric. Very cool talk. Let's see. Where does the organic matter come from, and how is it made?
Well, that's kind of the overarching question. So we know there's an abundance of simple organic ices that are within the interstellar medium and the outer solar system, but these aren't necessarily the complex organic. So essentially, we know that there is a mechanism that takes it from the simple organic ices to the complex organic materials that we know.
Right.
So it's just where that happened, whether in the interstellar medium or in the protoplanetary disk or inside the parent body. But essentially, the complex organics come from the processing of simpler organics through some kind of mechanism.
Cool. How different is the material you study from Earth material?
Chemically, it is very similar.
Mm-hmm.
Physically, I'm finding it's very different. And that's because the stuff I mentioned, coal, kerogen, these are mostly they're made through compaction processes in the interior of the planet, where these IOMs could be made more on the surface of ices just through basic irradiation. So physically, these are going to be like more less compacted, more fluffy kind of materials.
Right.
But chemically, they find them to be very similar, and that's why they use them as proxies in the models.
Cool. How difficult is it to get the samples as like to get on the list of people that will get the actual samples? Is that how difficult of a process?
I see. So for meteorite IOM for the meteorite IOM, it's more or less, you can just buy a meteorite. If you want,
Right.
We have a meteorite we bought, and that's one I'm processing from scratch to get a more abundant yield. Other ones, we have collaborators, they have stuff laying around. Mm-hmm. But say if we wanted to study the IOM from Ryugu or Bennu, that's going to be we're in the process. So
Right.
Step one, they want to know that we know what we're doing.
Right.
So we need to publish first. Once we've published and kind of made our point and shown we can, and that's the important thing, getting measurements on single grains because they only have so much material.
Right.
So once we prove we can do these measurements on very little material, then hopefully will give us some of the Bennu stuff. But yeah, the IOM, it's more or less who you know or how much money you're willing to spend.
Yeah, that makes sense. Can you do carbon dating with this kind of material?
I don't believe so. No.
Okay.
Because carbon dating's carbon 15 dating, and I think it's abundant in carbon 13.
Right.
But not the carbon isotopes that they would use for that kind of dating.
Has the solar system existed long enough for all IOM to come from only parent bodies?
So that's part of. So some of the most primitive IOM they found, they suspect is older than the solar system, which drives the ISM theory. But no, I guess we can't technically say that all IOM is going to be older than the solar system because there's no definitive, yes or no that all IOM comes from the same source.
Right.
So you could have IOM that was inherited and then some that was later formed. after the sun had already kind of got up and running.
Okay. I have a question for you. With the isotopes, and specifically isotope ratios, which one is the one that you find the most interesting to study?
I mean, for this IOM, the most important would be the D to H ratio. That's going to give you kind of be the most comparative kind of results when you can kind of look at IOMs and really see how they're very different. Once you start looking at the other ratios, that difference starts to kind of dwindle a little bit. But the D to H ratio and seeing how much that varies, I think is the more interesting result from those studies.
Cool. And then our last question, we always like to have a little fun. So are you supposed to be Isaac Newton there?
Yes, I am.
Yeah. Very. Well, thank you very much. Let's thank our speaker once again. All right, we're going to go on our 10-minute break, so that'll take us to 7:45. Remember, if you ever take a cool photo, please send it to samharthelio@gmail.com. All right, everyone. Let's settle back in here. Our next segment tonight is the Astronomy in the News, which tonight will be given by Aaron here because Jasmine's out of town. So we've got Aaron for Astronomy in the News.
Woo! I'm in the middle of dissertation hell right now. I'm in the final stages, the final throws. So we did a weird thing. Michael made the slides, and I'm going to read them off. So Spurs are not the only explosion in the South. Some of you may know what that's referencing. We're going to talk about astronauts to be named next week, Big Bang, black hole, Psyche ventures onward, and find out next. As in, like, that's an allusion to, okay. So the skies, around 10 p.m. for the month of June, Scorpius is coming over the horizon. Arcturus is almost directly overhead. And Michael wants me to ask, where are the planets? One of them is over the horizon at sunset. Isn't it like Mars? Oh, but at 10 p.m., yeah. There's no planetary parade anymore for this month. The planets had to go to sleep. And then, you know, at one point we got to get Caleb just online just to do this part. He just chimed, like, we just hear his voice, the disembodied voice of Caleb for the first timers. Yeah. Caleb was a long-time installment in Astronomy in the News, and he had a voice for broadcasting. He was made to do this, and he worked at the planetarium for years. If you ever run into Caleb Gamara, ask him about Hutchinson, Kansas. That man will talk your ear off for hours. But the sky, it's a very typical summer sky for June, around 10 p.m. No planets, unfortunately. Now, first news piece. Artemis 3 astronauts will be announced soon, Tuesday, June 9th at 11 a.m. Eastern or 10 a.m. here or 8 a.m. if you're in California. Streaming on NASA platforms, I'm guessing. Is there still NASA TV? No, NASA Plus. It's NASA Plus. Damn, they went to a streaming model too? On YouTube. Or Twitch. It's very hip of them. Very hip and cool and modern. So Artemis 3, it's going to test critical rendezvous and docking capabilities between the Orion spacecraft and commercial human landing systems needed to deliver astronauts to the lunar surface. So this is the next stage in building that moon base. Now to the reference in today's headline, New Glenn, big bada boom, catastrophic failure during a static test firing last Thursday? Yeah, last Thursday, around 8 p.m. our time. And then Launch Complex 36 must be restored. There was some extensive damage to the launch complex. And my favorite part is they were just selected to land on the moon. And then they blow up their rocket. That's not a good look. I bet Elon Musk is like doubly pissed. Like, and then they blow up, and then he blew up his own. Yeah. Rockets are blowing up. Billionaires are somehow making more money and whatever. But yeah, New Glenn aims to carry the future moon landers, including the Artemis 3 test. Someone's yelling at someone after this. And then a black hole as old as the universe. So using James Webb Space Telescope, researchers have mapped the motion and composition of gas orbiting a black hole in the center of Able 2744-QSO1. We all know that one. It's very common, household name. A tiny galaxy more than 13 billion years away. 13 billion light years. I mean, it's 13 billion years if you travel at the speed of light and you don't account for the expansion of the universe. Results suggest that the 15 million solar mass black hole predates its host galaxy. So possibly forming within the first second, within the first second of the Big Bang, and must have been immense from the start. So this throws the proverbial wrench into the system of cosmic origins and formations. That one's fun. Is this Able 27? That's the image of the galaxy they're talking about. The red one's somewhere. A, B. So, oh yeah. So there's a pixel, I promise, of the red dot. Monthly plug to go look at these images somewhere online with a nice display. They are fantastic. Oh, this is from ESA, the European Space Agency. Yeah, go find them online. You can Zoom for days. And then our last headline, Psyche passes Mars. Great pictures from Psyche. Closest approach occurred on May 15th. It was about just under 3,000 miles, about 4,500 kilometers from its surface. This was a gravity assist in its trajectory towards Psyche. So Psyche is named after the asteroid Psyche that it's going to go study it because they think it might be the core of a planetesimal, maybe to be determined. It's very metallic, which is super weird. Well, it's not weird that it's metallic. It's weird how metallic it is, which is why we think it's the core of a planetesimal, and that's why we want to go there. And so it takes a long time to get to the asteroid belt. You got to do a couple gravity assists on the way. This one was with Mars, and now on the rendezvous to its target in 2029. That'll be really fun. I'm excited. Are you excited? I'm excited. And then some upcoming events around town. SAAA, the San Antonio Astronomical Association, their meetings are on the second Friday. So the next one coming up is on June 12th. They are now at the Scobie Planetarium. Those are now where they will be for the foreseeable future. And then South Llano observing on the next day, Saturday, June 13th. South Llano is about, 2 hours north, up I-10. And then, of course, after dark. You want to look at the stars, you got to go, you can drive at dark. You got to drive at dark at some point, but I don't like I-10 at dark. Ask me why. And then glorious pictures. Some of them included the emotional Wemby, the alien, after Game 7 versus OKC. And on the left, we have Andromeda through gas and dust. Oh, that was the NASA APOD, the astronomy picture of the day. And then M77, a glorious new JWST picture of the month from ESA. And that's the astronomy in the news. And then Erica is going to introduce our next speaker.
All right, Jonathan, you want to come on up? And then the other mic is just... All right, so our second speaker today is Jonathan Gasser, who is a postdoc at Southwest Research Institute here in San Antonio. His research is focused on heliospheric science, aka heliophysics, where he analyzes observational data of the solar wind and of energetic neutral particles from IBEX and IMAP missions. He's also involved in development, experimental testing, and calibration of new generations of space particle instruments. Jonathan obtained his PhD at the University of Bern in Switzerland with a dissertation titled Towards Better Calibration of Space Instrumentation for Measurements of Energetic Neutral Atoms. He also holds a master's degree in theoretical physics with his thesis on axion dark matter interactions in the framework of thermal quantum field theory. That is a heck of a switch, sir. All right, so like we had earlier, we have a drinking word for all of our speakers. So Jonathan, what is your speaking word? Or drinking word, sorry. Apparently I've been drinking too much. Oh, yeah, you got to turn it on.
Okay, good evening, everybody. My drinking word for today is going to be boundary.
All right.
Boundary.
And there is... All right, take it away.
Thank you so much for having me. Yeah, to start with a brief disclaimer, I put in the title, and I only realized today that on the web, on YouTube, we find videos or contributions with pretty much exactly the same title, except for New Horizons. This has no connection. But yeah, I'm gonna take you on a virtual journey today to the edge of the solar system. But first of all, let me introduce myself a little bit. I'm a postdoc at Southwest, as Erica has mentioned. I came here about 2 years ago from Switzerland. And for those who were here last month, Switzerland takes about 3.7 times place across Texas. So it's a tiny country comparatively, except if you zoom in for the third dimension, some of the top Alps are above 4,000 meters. I guess Guadalupe Peak is around 2,800 meters. And yes, before you will ask me, I also play the Alpine horn in my free time. But set that aside, I'm a heliophysicist here and space instrumentation development. I'm going to talk a little bit more about the heliosphere once we get out there. Okay. Every good journey starts with the first step, and even better so with planning. And here is sort of the roadmap of the journey we're going to take today. You see on the left, in the center of the solar system, of course, the sun and Earth at 1 astronomical unit. Then you got all the planets. So that Saturn is about 10 times further away. Then beyond the planets, there is a region that is called the Kuiper Belt that is populated with many, many small objects. We'll see that. And somewhere between 50 and 100 and some more units, there's going to be some of the boundaries of our solar system in terms of plasma and in terms of objects that are there. And outside that, we are in the interstellar medium that is reaching tens of thousands, well, actually all over, but tens of thousands of AU away. We again come through a region where there are many, many icy objects swirling around. Actually, and this is called the Oort cloud. Actually, no one has seen the Oort cloud, but its presence has been determined basically from long-term period comets that appear to originate from around that distance from the sun. And if we go out even further and further, we are talking light years now, about 4-point-something light years, we reach the next stars, Alpha Centauri. And this is still, all of that is still very local within our galaxy or within the interstellar clouds around the solar system. So, I meant to mention Pluto is our primary destination of the New Horizons spacecraft, but that's what I'm showing here. New Horizons was selected as a primary planetary mission to the Pluto. At that time, Pluto was still a planet. It was selected in 21A, and the PI is Dr. Alan Stern from Southwest, and the whole mission and spacecraft was developed together with John Hopkins Applied Physics Lab. And of course, from 21 to 2006, there was most of the work going in developing and building the spacecraft. You see on the top. And then finally, January 19, 2006, New Horizons was launched on a Atlas V rocket. Unfortunately, they just missed my birthday by 1 day. And it was the fastest launch of any spacecraft so far. So directly from Earth orbit, they injected it into a Earth escape and solar orbit trajectory. And then New Horizons went out further, and after just over 1 year, it passed by Jupiter. It made a gravity assist to boost the speed even more and set it in the right direction towards Pluto. You remember Pluto was much further out. Pluto will be at around 35 astronomical units. And after Jupiter gravity assist, for most of that travel, the spacecraft was in hibernation, meaning asleep. So they only did annual checkup, kind of making sure they can still communicate, all the instruments are still alive, but not much was done except waiting. Yeah, we take that time to sort of look into what is actually on spacecraft. So New Horizons carries a wide field camera lorry that is on the bottom here. It has 2 imaging spectrometers, Rolf and Alice, that can measure spectra in the visual, in the infrared, and ultraviolet range to observe spectroscopic properties mainly of Pluto's surface. And then SWAP and PEPSI are 2 plasma particle or charged particle detectors to sort of investigate the particle environment, the space environment around Pluto. New Horizons also carries a student dust detector that is hidden here from the view that can measure dust particles that impinge on the spacecraft while it's traveling outward. And of course, every spacecraft needs, especially going that far out and planning to go that far out, needs a strong radio antenna, REX here, and the RTG up here is the radio thermoelectric generator, so essentially the energy source. And well, it's been a long journey. After 13 years of total mission time, in 2019, New Horizons, that's wrong. I meant in 2014. New Horizons was approaching Pluto and received a wake-up signal from Earth about half a year prior to the closest approach. And in that time, they took many images, mainly Rolf and Alice did this. This is an example of the Pluto and its largest moon, Charon, from far away. I believe it was still in February, with pretty low resolution still. And well, the same image, sort of one of the best or most popular images of the Pluto system, Pluto and Charon. In July 2015, they passed by here, and basically all the primary mission, all the instruments were taking data through these, I believe, couple days, mainly where they were close in the system, took many photos, spectral data, particle data, and all of that then took them more than 1 year to downlink all the data through REX. And so, yeah, Pluto, before New Horizons, it was known, I should mention, at launch, it was still considered a planet, but a couple of months later, Pluto was relabeled a dwarf planet, basically because the International Astronomical Union defined more precisely, or defined what is a planet and what is not a planet. Nevertheless, the object remained the same, and New Horizons had led to many, many discoveries. One is that Pluto appeared to be geologically very active. So you see the white range area, and you see many, many craters all over, but the craters are not really evenly distributed over the surface. So they're kind of clustered here, and then on the white patch, you see no craters. That means this white surface part has to have been renewed within relative short time of couple of million years, short time in geological time scales. And that was sort of unexpected and unprecedented that an icy world thus far away shows that type of activity. The other thing was about Pluto's very thin atmosphere. You see in the middle a eclipse type picture with the atmosphere reflecting sunlight, and in the zoom in on the bottom right, you see there is layers of haze going through this atmosphere. So apparently there is some sort of process of weather also on a dwarf planet like Pluto. So this mission has expanded very, very much about what we know about Pluto specifically, and expanded the boundaries of what has been known. Too late. Charon, it appears Charon is kind of one of the darkest objects in the solar system, and of course New Horizons also investigated a lot about Charon. I'm not going to talk too much about Charon, I just want to mention it. But Pluto also has 4 other moons, smaller moons. Some of them were only discovered short before New Horizons, and that is Nix and Hydra on the left side. You kind of see Nix and Hydra, New Horizons, so they share the initials. And then 2 even smaller objects that are not even very resolved here, Styx and Kerberos. So it appears Pluto has been able to capture these and bound it to its orbit. With that, New Horizons' primary mission has more or less concluded, but of course the journey goes on. The New Horizons mission has just shifted in a second phase, that is exploration of the Kuiper Belt. As I mentioned, the Kuiper Belt is a region close to the ecliptic, that is populated with different icy objects, dust, some dwarf planet like Pluto, and the minor bodies all over. And it spreads from 30 AU, so around Neptune's orbit, out to 50 or even 80 astronomical units from the sun. Today, in parallel to the New Horizons mission, there has been a search of those type of objects to find candidates. Where could New Horizons possibly fly by close and take a very close look on one of these objects, because they haven't ever been observed close. And this led to more than 100 known carbon objects today. And why are they so interesting is, as Eric mentioned earlier also, these type of objects are also sort of an archive of frozen matter that supposedly lasted from the very early times of the formation of the universe and are kind of almost unaltered ever since. And finally, the Kuiper Object Survey search has identified an object that New Horizons eventually passed by in 2019, and that is this guy here, 2014 MU69. So you see, it was only discovered 5 years prior to the visit of New Horizons. And it appears this object has, first of all, it's a bimodal object. So it appears it was formed by a very soft collision of two parent bodies, and its surface is very smooth. There is not much weathering and changes, craters also that you would see, for example, in asteroids. So we are pushing out further the boundaries of the solar system, and especially the region where we see planets, where we see small objects. Before we go on, I think that the next kind of boundaries are not necessarily about objects orbiting, but are more in the way the solar influence is transmitted in terms of the plasma. Let me explain that. So this is referred to the heliosphere, and it's turning in a second extension, a mission extension that is more and more about the helio science that they can do out there. As it is traveling, you see here, away from Arakoth, away from Pluto, into the even, I would say, emptier and darker space. It's at 64.8 AU right now, and the science that is performed here is covering an element of both the planetary, heliophysics, and astrophysics disciplines. So let me give you the overview. The heliosphere basically is a very vast plasma bubble that is surrounding the solar system, and it creates, or it establishes, two main important boundaries here. So first thing is the sun in the center with the planets is emitting solar wind. There is a constant stream of charged particles, mainly protons, some alpha particles, and they carry along the solar magnetic field out in all directions. So this is not a 2D, this is a 2D cross section, but the bubble is 3-dimensional, of course. And then as the solar wind goes out and carries this magnetic field with it, at some point the solar wind drops below the sonic speed, and that's where this roundish boundary forms that is called the termination shock. So it's a plasma shock, and the shocked plasma then travels further out and starts to interact more and more with the gas of the coming from the interstellar medium here on the left that is coming toward this heliosphere as the sun moves in the direction in one direction around the galactic center. And the second boundary here is where the solar wind shocked plasma sort of here is connecting or is interacting with the interstellar medium, and this there is because of the magnetic field carried along, there is a no mixed zone, so it's a real boundary in terms of the plasma. And spoiler, New Horizons is not really the first mission that went out there. We had Voyager mission, Voyager 1 and 2, that are out there past this heliopause boundary in the very local interstellar medium. And New Horizons right now is still inside the termination shock, and the termination shock is kind of the next boundary that is heading to, and that we want to know when is it going to arrive here. So very briefly, Voyager 1 and 2 are kind of the rock stars, or the ancient wise identities in terms of missions. They were launched in 1977 as a planetary missions. Voyager 1 was destined to visit Jupiter and then Saturn, and then kind of took off of the ecliptic plane in the northern, sort of 30-degree north, and continued moving outward. And the Voyager 2 was launched 1 month earlier, but was on a slower trajectory and reached Jupiter, then Saturn as well. But instead of departing from there, it also visited Uranus and Neptune for the first time. And two of the main results or benefits we had from the Voyager are these two. The other one was sort of the last picture taken by Voyager 1 from off Earth. So this pale blue dot here in the center is planet Earth. Voyager 1 is the fastest moving spacecraft we have outside of Earth's orbit, and is the furthest object away that was sent out by humans. Voyager 2, on the other hand, discovered Neptune, discovered geysers, for example, on its largest moon, Triton. And this pale blue dot was discovered by Voyager, which appears to be a sort of a very large atmospheric storm, similar to the red dot on Jupiter. And after planetary encounters, both Voyagers went out and encountered the termination shock. Voyager 1, as the first probe, in 24. And the termination shock at Voyager 1 was at 94 astronomical units, so almost 3 times as far as Neptune's orbit. And the heliopause, so the boundary between the solar wind and the interstellar medium, it crossed it in 2012. And I mentioned it's the farthest object zone right now, around more than 170 astronomical units outside the solar system, if you consider the plasma, the heliopause as the boundary. Voyager 2 is trailing, but not by far. It reached the termination shock 2 years later. It reached the heliopause 6 years later. It's been a little bit slower, you know. And it's also outside the heliopause. Why do we know these both probes are actually in the interstellar medium? There has been a little bit debate in the community, but most scientists agree that what you see here, Voyager 1 particle measurements were at a certain level, then they do something weird, and eventually they drop to close to zero in terms of tens of keV electrons they observe, whereas the magnetic field wiggles around here, 0.2, 0.4, and then after this sharp rise here, it's been very, very steady. And basically the same story you see at the Voyager 2, not a very clear drop, but still a sharp drop, and the magnetic field rising sharply and then going relatively smooth. Now the question is, in terms of New Horizons, where is this termination shock? Voyager 1 says it was at 94 astronomical units. Voyager 2 says it was at 84 astronomical units. And both spacecraft go in different directions. So this here is a model of a heliospheric magnetohydrodynamic model by Eric Powell, where he depicts the termination shock and color codes the distance in different directions from the sun. So apparently Voyager 1 and 2 show different directions where they head, and they encounter the termination shock at different distances. And New Horizons is going to be close to the ecliptic here, and it's going to, according to that model, it should encounter the termination shock even earlier. So closer in than 84 IU. But also, second problem is this termination shock is not just a steady wave. It's dynamically moving in and out as a response to changes in the solar wind, pressure. And therefore, this adds to trying to predict or foresee when and where New Horizons is going to cross that boundary. So we did take solar wind pressure data that were measured at near Earth, and what is needed, we sort of expanded and predicted, forecasted, how is this solar wind pressure going to change in the next 10, 20 years? And then so the solar wind, about 1 year later, will guide how this termination shock moves in and out. I think that should be flipped. Yeah. So the question is then, how much does the termination shock move when the solar wind changes? And depending on which model or which calculation we follow, this can lead to 3 or 4 different scenarios here. So if the termination shock did not move at all, we would see it crossing around 90 astronomical units. And then if we assume a relatively strong motion in response of a termination shock of the solar wind of this termination shock boundary, this is in time, it's going to move out by 10 to 20 astronomical unit and coming back in, whereas another model sort of predict a very minor overall change in the response of solar wind, so it could only vary 5 to 10 astronomical units. So overall, it turns out it's not an easy task, and it's not very clear where New Horizons will really see the termination shock. And but for the mission planning, because this New Horizons is the only spacecraft that we have out there now and for at least 10, maybe 20 years. So science of the termination shock and finding out what are the processing governing that in terms of the plasma environment is going to be a sort of once in a career chance that the team has now. I skipped one slide here, an alternative way to try to determine the termination shock and predict where it is when we look at particle in particle detector, energetic particle detector measurements along the journey here from Voyager 1 and 2 in red and blue. So they observe a decrease in energetic particles as they go away from the sun, and then even outside Neptune and Pluto orbits is kind of leveling off. And then short before the termination shock was finally encountered, they sort of started a rise, to see a rise in energetic particles, again, that are coming from the outside. And so New Horizons, of course, doesn't have these measurements here, but it has energetic particle measurements all the way from Earth to Jupiter to Pluto and on. And by comparing the profile of these instruments from Voyager, what the Voyager had observed and what New Horizons is observing, Romina Nikokor has determined New Horizons could reach a termination shock somewhere between 68 astronomical units, so that would be pretty close in maybe 2 years, or further out at around 80 AU. So this is the next boundary New Horizons is going to encounter. And after that, there should still be enough resources in terms of energy, in terms of the bandwidth that it could continue its mission to eventually become the third objects to leave the plasma environment of the sun, of the solar system. We'll see. The limits of this mission basically are how much radioactive power is still left, when is it going to reach the sort of the range that our communication, the deep space network, is covering, and any mission running also need to be funded for operations, for science. So these are the three limits that all three missions actually, but in particular New Horizons is facing. I think with that we are closing to an end, returning back on Earth from the edge of the solar system. Just let me make one more point. What next? There has been a new mission concept specifically that plans to send out a probe. It's called interstellar probe, directly from Earth, either via a Jupiter gravity assist or even a gravity assist at the sun, to directly go into the interstellar medium and target the plasma and the dust and the composition of that medium up to 1,000 AU away from Earth within 50 years of the mission. So, but again, this is going to take a huge effort, and probably is not going to be realistic unless it's going to be a joint mission between different disciplines from astrophysics, planetary science, and heliophysics. Remains to be seen. Yeah, so thank you all for coming, and happy to take questions.
All right, thank you, Jonathan. Our first question is, okay, thinking about the choice to make New Horizons a flyby, why was that the most selected choice as opposed to trying to stop?
Why not go into orbit at Pluto? That would be fantastic. You have to know, though, even orbiting a planet like Jupiter, which is probably 10 times closer, requires much longer travel times, because when you do a flyby, you can shoot more or less into a trajectory that's heading directly to the target. You don't have to worry about stopping there, whereas trying to orbit a planet, you need to decelerate pretty substantially to get into an orbit around a planet. And then, given the small size and the faraway mass and the faraway distance Pluto has, this would probably have taken forever because you cannot approach that fast and decelerate that fast, because it consumes all your energy, and then go into orbit. So a flyby was basically the only viable option.
Yeah, very cool, thank you. Is the termination shock location thought to be dependent on the solar cycle?
Yes, sir. Yeah. Solar wind parameters, the pressure, the magnetic field, the speed, etc., density, they all depend on the solar cycle. And then the termination shock also depends in part on the solar wind conditions. So the response of the termination shock is delayed in time compared to the solar cycle at the sun, because there is travel time even for the solar wind.
All right, and then our last fun one. So Voyager had the records, the golden records, right? Does New Horizons have anything fun to let the aliens know who we are?
I believe I put up a slide of the golden record. I didn't show the backside. So on the on this disc on the record, there is recordings, sort of type vinyl plate recordings of noises of sounds of Earth, and on the front side, which is not that side, there are symbols in sort of markings. It's kind of hard to describe, but it's supposedly triangulating in some way the position of Earth compared to nearby standard stars called pulsars, which have a given pulsating rate in their light, in their brightness. And so potentially if alien life existed out there, intelligent alien life, and they would find and understand the message, they could determine where is Earth.
All right, very cool. Let's thank our speaker once again.
Thank you.
All right. If you all, for whoever can't stay for trivia, thank you so much for coming tonight. We love to have you, and we hope to see you again in July. Our next AOT is July 1st, and I guarantee you it will not be the same night as a Spurs game. But for those of you who can stay for trivia, we'll come around with the sheets and writing utensils. And as a reminder, please, maximum group size of 4, and do not use your phones. Oh, and I forgot to mention, if anybody's interested in buying a shirt, feel free to come on up and get a shirt. We have all sizes that you could want. And remember, cash or Venmo. Yes.
All right. Does everyone who's playing trivia have a sheet and a writing utensil? Going once. Going twice. Sold to the lowest bidder. All right. Question 1 for tonight's trivia. Score update. Spurs are up 50-48.
Almost halftime. Oh,
52.
52. Nice.
Almost halftime. Question 1. Wow, that's fast. Relative to Earth, what was the speed of New Horizons just after launch? 16.26, 16.76, 17.26, or the best year for America, 1776, 17.76 kilometers per second. Now,
Merca.
just after launch.
And this is memory recall. Jonathan had this on his slides, so yeah. I mean, think about it, folks. This thing got to Jupiter in a year. You want to talk about fast? That's 4 AU in the blink of an eye.
20 U in 3 months on average. Jupiter's far.
Well, at least 4 AU. Minimum 4. Yeah. No, I know how. Yeah. 4 point something.
4 in a straight line. It's on a curved trajectory. Don't come at me with the orbital mechanics.
All right. Question 2. Very impactful. The Chicxulub
Chicxulub.
crater at the Yucatan Peninsula is the largest impact crater known. However, there is an impact structure that is larger, but much of the crater has been eroded away. What is this structure called? And then in bonus, right next to it, where is this structure? So we have A, the Sudbury structure, which if anybody watches Shoresy, you'll recognize Sudbury. B, the Papagai structure. C, the Vredefort structure. Or D, the Acraman structure.
Largest impact crater on Earth.
This is Earth-based.
All right. Question 3. Nomenclature. What type of classification is Arakoth? Now, the classification of the object itself, is it A double-double, B, a contact binary, C, kissing rocks, or D, an equal mass binary?
All right. Question 4. Would you like a sample? How many asteroids have returned samples on Earth? Return samples, okay? We went to the asteroid, scooped a bit, and came back. That's what that means. Oh, yeah.
We asked.
1, 2, it's me. That's why I'm specifying. It means we sent a spacecraft, it went yank, and it came back. I don't care. I'm a scientist, not an English. It's like
Run a science communication outreach program.
no, I know.
Get you.
It's well, it's like old Bones from Star Trek used to say, "I'm a doctor, not a physicist." In this case, I'm a physicist, not a prosist.
Prosist?
I don't know if that's it. Is it 1, 2, 3, 4? Yeah. What? Yeah. It's like, has anybody lived in a state with bottle deposits?
With what?
It's like that, you get it back and then you get the nickel back. Not that nickel back. If you haven't lived, you can see it on cans and bottles. States, especially in the Northeast, when you buy a bottle or a can, you get charged 5 cents extra per bottle or can, and you get that 5 cents back when you return it to the proper machine. So it's like you're returning it, but yeah.
All right, question 5.
Pinkies up.
Finish that
getting
lyric,
fancy.
Michael Vella's edition. Composing it prior to the discovery of Pluto, Gustav Holst's The Planets is an orchestral suite featuring our solar system's planets as movements. Which movement is Neptune?
Yes. If only Pluto had been existed, we would have gotten more music. Yeah, yeah.
All right.
All right.
Question 6.
We're going long distance here. All right, New Horizons currently has an extended mission out to 2029, and hopefully it goes longer because we want the heliophysicists to have their science. So call NASA and tell NASA to get their act together. How far from the sun will it be in 2029? Is it A, 60 AU, B, 70 AU, C, 80 AU, or D, 90 AU? $2029.
Does anybody need a question repeated?
1, 2, 3, 4, 5, 6. Going once. Going twice.
All right, everyone got an answer?
Bonus.
All right. Bonus question. Bonus question goes in the bonus section because that's where the bonus goes. What is the progression of names a space rock has as it falls to Earth? The options are meteor, Michael's mantelpiece, meteorite, asteroid, bolide. So put those in order as the space rock is falling from space to Earth.
Answer on, put each one on each row. You have plenty of rows. Do not do answer, comma, answer.
If you've been to flying saucer, do the opposite of that. Stack them. Not answer, comma, answer, comma, answer. All right. If no one needs a, if, if no one needs a question repeated, when you are finished, please bring your answer sheet and the pen, if we gave you one, up to the front,
Yes, if you took a pen, please return those.
please. We lose about one a month, so we're running low.
Yeah. It's a war of attrition. This bonus question, credit where credit's due, is brought to you by Tracy Becker.
Nutrition? What about RFK's nutrition?
All right, everybody, before we go through the winners, we will go through the answers.
Score update 55-48.
We're back from half.
Answers. How fast was that spacecraft going after launch? Oh. We had,
Uh-oh.
hold on, a late submission.
Oh my God, everybody's getting... A, C, B... I should be a physics professor. Asteroid, meteor, bolide, meteorite, Michaels. Okay, that's pretty good. Asteroid, bolide, they're the same. But none of them got the bonus.
We're the 2/3. All right. I mean, they can all just get those.
Yeah, we'll just give everybody.
We have plenty. They can let them. We can let them.
Go at it.
Yeah. All right.
Okay. We're
Changed
ready.
absolutely nothing. Question 1. Wow, that's fast. How fast was that spacecraft going? 16.26 kilometers per second. Way too fast.
This was right on Jonathan's slide. My goodness.
Would have been great. It was 1776.
That's how tall the Freedom Tower is.
Yeah.
Um,
On a warm day.
Question 2. The largest impact structure is C, the Vredefort structure, which is in South Africa.
Fun piece of trivia, because we
We're
have
just gonna
to
give-
delineate things even further. An ancient impact crater, even though they're all ancient, is called an astrolabe. There's one out in West Texas when you're going to Big Bend. Astroblem, thank you, Astroblem. There's like a sign, and it just says, like, when you're going out to West Texas, like, Astroblem. And it's like, what is that? And you don't realize you went down like 10 feet. It's because it's super eroded. I don't know. It gets weird in geology. Is it? Because it's like flat. It's like flat. I believe you, Mark. Question 3. Don't offend me. What's the name? What's the nomenclature for Arakoth? It's not highlighted. It's a contact binary. It's B. Oh, we didn't change the answer. That was Michael's
Oh.
original D. And then I threw in
Actually,
a
I think
science
Sam
one.
put that one. That one was Sam.
What, burn up?
Yeah.
Oh. I put
I was kissing rocks because look, they are kissing rocks.
Now kit. It's B, contact binary. Because it's a binary that's contacted.
I vote we change it to kissing rocks.
And then,
And double double was a reference because tonight's basketball.
oh, I thought it was
See,
in
I
and
know
out.
basketball terms.
I thought in and out.
Yeah. All right, question 4, which was about how many samples do we have? The answer is 3. And it is Itakawa, Bennu, and Ryugu.
Yep. Yeah. Itakawa was like very, very little. I have. Maybe? Yeah. Yeah. Question 5. Finish that lyric. Oh, what movement is Neptune in the planets 7?
So, Horst did not include Earth in his movements. So there were only 7 to choose from. So Neptune was last. The order was he started in the terrestrial planets, he went out in. So he did Mars, Venus, Mercury, and then Jupiter, Saturn, Uranus, Neptune. Those are the movements. Did he forget the Earth? I mean, I guess he thought that, every other symphony that's been done is already Earth. So,
Earth is included because it's played on Earth, I guess.
That's true, and it's based on astrology. We don't have Earth astrology on Earth. I mean, I guess if you look down enough.
Yeah.
All right, question 6. How far will New Horizons be in 2029? Roughly 70 AU. Yep. It's working its way out there.
And then for the bonus,
There's a B.
what is the progression of names a space rock has as it falls to Earth? Asteroid, meteor, bolide, meteorite, and then it goes on Michael's mantelpiece.
Yes, at front and center. A nice little asteroid conversation piece when people come over.
Now,
You need
this
a
is all
microscope.
hypothetical because A, I don't have one with me. I don't have a meteorite with me. They're all at home with my parents. And B, I don't have a mantle. How many fireplaces are there in San Antonio? Not
You
a
have
lot.
a house, quite a bit.
Yeah. Well, yeah.
Jasmine's apartment had a fireplace.
Yeah.
It was really her first one. It was really nice.
Oh,
Also a fire hazard, but whatever. That's nice. I like fireplaces.
All right. All right. So tonight there wasn't a lot of parity in our answer, like how people did. So what we're going to do is we have a bunch of these postcards from the planetary data system. And so because we have a boatload of them, we'll just be very generous. We have a lot of, today's third place prize is really just your all honorable mentions. So you can all come up and get a postcard. We have, hold your applause to the end, Marco, Voyager 1 to Wemby, Wolverine Warriors, and the neighbors. Please come up and get your postcards. Huh? There's too many of them. I know there's nobody to applause. Woo! Can somebody showcase a poster?
They're all the same. Yeah.
All right, and then tonight's second place prize each team member will get this very cool Lowell Observatory mini poster from Flagstaff, Arizona. The winner of the posters are Team Gunk. Congratulations, Team Gunk. Where's Team Gunk? Is that Eric?
No,
Did he step out of the?
they might have been the dudes that just left.
All right. And then the winner tonight will win each team member will be leaving with a beautiful lunar orbiter. What? Uh-oh. Beautiful lunar orbiter print. Thanks to Robert Reeves. My anus. No, Uranus. Woo! Come on up. Round of applause for our winner. Congratulations. Yeah, they're all four identical. Well, the Lowell Observatory ones might go back in the stockpile. All right, our next AOT will certainly be on July 1st, which is a blessing and a curse, because that's so soon. Special thanks, as always, to Blue Star. Thank you for having us. And thank you to our wait staff. You always do a great job. UTSA and SWIRI for their continued support, and especially SWIRI because they're going to help us get our stickers. So sign up. Sign up for our email list if you haven't already, and our socials as well if you haven't already. We'll see you all on July 1st. Go Spurs!